Hello, I am Arthur Sleuters, a PhD student at UC Louvain, and I will be presenting our paper on hand gesture recognition for an off-the-shelf radar by electromagnetic modeling and inversion. In this work, we use the Wallabot developer, which is a portable and off-the-shelf frequency-modulated continuous wave radar sensor. Its European version, which we selected for this paper, operates at frequencies between 6.3 and 8 GHz, while the US version operates at a wider range from 3.3 to 10 GHz. The Wallabot has 18 different antennas, including 4 acting as transmitters, and provides 2 different profiles. When configured in the first profile, it senses motion using 40 different pairs of antennas at about 20 frames per second. In the second profile, the Wallabot uses 12 antenna pairs for sensing motion. It reaches a higher frame rate of about 40 frames per second. We selected the second profile to benefit from this higher frame rate. So why did we select the Wallabot? First, from a technical point of view, the Wallabot is relatively inexpensive compared to other radar sensors. In addition, its portability and off-the-shelf availability make it a great candidate for using it in future mainstream applications. It also offers a wide range of configurations, including up to 40 different pairs of antennas, and its C++ API allows for easily retrieving raw radar data from the sensor. The Wallabot is also interesting from a scientific point of view, as it has been the subject of research in domains such as activity recognition and material identification. However, as of now, we are aware of only one paper where the Wallabot is used for hand gesture recognition. As such, it leaves many avenues to explore in gesture recognition. Radar gesture recognition comes with several challenges. A first challenge is that radars are quite sensitive to noise and clutter. For instance, the signal from a user's hand can be hidden by the parasitic signal from antenna effects, such as internal reflections within the radar itself and direct transmission from a transmitter antenna to a receiver. This parasitic signal can be seen at the top of the figure. It's very strong and completely hides the hand reflection. Other sources of clutter are reflections caused by background objects such as walls and furniture. It is thus very important to clean the data before it's used for gesture recognition. A second challenge of radar gesture recognition is the high complexity of radar data compared to data generated by other sensors, such as accelerometers or skeleton data. It can be difficult to identify complex motion from raw radar signal, and this complexity can be multiplied by the number of receivers. For instance, the Wallabot can provide signal from up to 40 different antenna pairs, multiplying the complexity and the size of the data by the same amount. As a consequence, simple techniques such as pattern matching algorithms may not be suited for radar gesture recognition without first pre-processing the data to reduce its size. In this paper, we detail an 8-stage pipeline for radar gesture recognition, which offers a solution to these two challenges. Steps 2 to 6 address the first challenge, the sensitivity of radar to noise and clutter. We apply the radar equation to the raw frequency domain signal in order to remove antenna effects such as internal reflections and transmissions, as well as multiple reflections between the antenna and the target. This step requires a model of the radar antennas, which can be created by recording radar signals at various distances from a large sheet of metal. Then, we subtract the background from the radar signal to remove static reflectors, such as walls and furniture. This makes the signal independent of the environment. Finally, we truncate the signal in a time domain in order to keep only the signal that's relevant for gesture recognition. In our case, we ignore everything past a certain distance of the radar. For instance, people moving behind the user should not be taken into account. Steps 7 and 8 address the second challenge of radar gesture recognition, which is the complexity and size of radar data. We first extract two parameters from the radar signal using data inversion: the distance between the user's hand and the radar, and the relative permittivity of the medium defined by the user's hand. The distance provides information about the position of the hand in space, while the permittivity gives an idea of the configuration of the hand, for example, making a fist or opening the hand. Then, the distance and permittivity data are filtered to limit the impact of errors in the inversion process. These errors can originate from a low signal-to-noise ratio, or if multiple objects, for instance another person, are visible in the field of view of the radar. This pipeline has been evaluated on a custom 16-gesture dataset recorded with 3 different devices: a Wellabot, a custom horn antenna, and a leap motion controller for comparison. The dataset contains 5 templates for each gesture class and for each device. For the evaluation, the Jackknife Recognizer was trained with up to 4 training templates and tested on the remaining templates. We compared the results at 4 different important stages of the pipeline. For each test, we recorded the execution time and the recognition rate. We can see that on the raw frequency domain data, accuracy already reaches nearly 80%. After filtering, the accuracy increases by about 5% and reaches 84.5%. After the inversion process, accuracy drops by about 20%, which is expected as there is some loss of information. In fact, the size of each gesture is divided by a factor of more than 30 compared to frequency domain data. Finally, after filtering, accuracy increases to nearly 71%, which is relatively high considering the reduction in data size, and only about 15% lower than on frequency domain data. However, we expect accuracy to improve even further with more training templates. So now, from the results of our testing, we identified a series of guidelines to follow to achieve better results in radar gesture recognition. First, we should favor gestures with a highly differentiable surface of exposure, such as showing a flat hand and showing a fist. On the other hand, gestures such as showing one finger and showing 2 fingers are more difficult to differentiate and result in lower recognition rates. Then, we should favor gestures with motion parallel to the radar beam, such as pushing or pulling. On the other hand, gestures such as swiping left or right will be harder to differentiate. We should also favor a larger number of training templates. In our testing, the best results were obtained with 4 training templates, but more templates could result in even higher accuracy. And finally, it's important to carefully select the combination of antenna pairs used for gesture recognition, as the execution time increases with the number of antenna pairs, and some combinations of antenna pairs perform better than others. Thank you for your attention. For more details, don't hesitate to check out our paper.